This is the first in a three-part series where we'll be talking about plate tectonics and its influence on the environment. We're going to take this in a historical perspective, marching through time from the beginning of the solar system up until close to the present. And I'm going to focus on this talk for the most part. I'll get to plate tectonics at the end, but on the conditions that prior to plate tectonics that set the environment for the existence of plate tectonics. As far as we know, we know for sure that Earth is the only planet that has plate tectonics now. It's possible that Venus used to, doesn't appear to have plate tectonics now. And it also seems to be the only planet in our solar system that actually has life, although we're looking at Mars and may eventually find it there. So if we look back to the very oldest material that we have from the Earth, and this was just discovered in the last several years, the very oldest materials come from Australia, from Western Australia, in a place called the Jack Hills. And the oldest materials we have are tiny little crystals of a mineral called zircon. This mineral is right here. This grain is about the width of a human hair. Tiny little crystal. This is the oldest bit of material that we have that's actually native to the Earth. It crystallized out of a magma. You can see the growth zones here, and the core of it is the part that's the very oldest, 4.4 billion years old. The Earth formed 4.56 billion years ago, so this isn't too long after the Earth formed. As you can imagine, this tiny little material, there's a lot of interest in it. A lot of people have studied it in various ways, and even though it's this tiny, we can learn quite a bit from it. And what we can tell from this crystal is that there were probably already continents present at this time, 4.4 billion years old. This crystal of zircon crystallized at about the same temperatures from a magma that they crystallize today from magmas. And by looking at the oxygen isotope composition, it looks like there was already surface water, possibly oceans at that time. So how did we get there? We know this is an important aspect of the Earth, is that it has been more or less like it is today. There have been some pretty large changes, but on a large scale, on a planetary scale, if we look at other planets, the Earth has been a lot like it is today for a very long time. And that's one of the conditions that makes it fit for life. So if we look at a larger scale, the scale of events here, going all the way back to the Big Bang, which I know you can't see here, so I made it a little bigger. This is where the universe formed. All of the matter, the fundamental particles that matter is made of, we think were created in the Big Bang. Hydrogen and helium atoms were created then. As the universe expanded, it cooled and became dark. But then after a few 100 million years, the first stars started to form and brought light back into the universe and brought the first heavier elements. So the Big Bang created hydrogen and helium, but it wasn't until the first stars formed that heavier elements, the stuff that our Earth is predominantly made of, began to be formed. And those formed by fusing lighter atoms together in a series of stages to make heavier and heavier elements. And that can only happen at very high temperatures, very high pressures, which are found in the interiors of stars. Sometime later, these early stars, which were very big, maybe 1,000 times the size of our sun, went through an evolution as they burned these different elements in fusion reactions that created higher and higher temperatures. A lot of energy is released. And they went through their evolution. Stars go through an evolution. They went through that fairly rapidly. And the first supernovae of these very large stars, they reached a point where they exploded. That explosion creates even more elements, the heavier elements, and it spreads them around through the universe. So one theme here is that you have matter being formed, it organizes into stars, it explodes again, and then it can go through successive stages of star formation. We'll see themes like that with the Earth too. There are cycles in the Earth. And then here's our solar system, which formed 4.56 billion years ago, fairly late in the history. and the Big Bang we think was around 13, 14 billion years ago. Okay, how do we learn about the origin of the solar system? One thing that we can do is we can look through telescopes at places where stars are forming now or in the very recent past. And what you can see here's a cluster where a large number of stars are forming. None of these are older than about 300,000 years old, so these are new stars. Some of them have already formed a star and planets, but some of these still have a dust cloud around them that you can see here. And that's what we think the solar system looked like very early on. Before the planets formed, there was a cloud of dust around the sun as it formed that gradually coalesced into planets and smaller bodies and to create the solar system as we know it today. The other piece of information that we have about the early solar system, the primary information that we have, comes from looking at meteorites. And Ralph Harvey, who some of you may have heard speak in this series last year, runs a program where he goes out and collects meteorites. And many of the meteorites that scientists use come from this program. They're curated at the Smithsonian Institution, and they're studied all around the world. And the most abundant type of meteorites that fall to the Earth are chondrites. And these are a kind of meteorite. These are the most pristine samples we have from the early solar system. The planets have gone through many active processes that didn't affect these. These were never incorporated into large bodies that partially melted or heated up very much to change their compositions. So they're formed of the materials that came out of that dust cloud. There are little droplets here of quenched melt that were part of that early dust cloud. There are bits of metal. There are inclusions that are some of the very earliest things to precipitate out from the solar nebula. So we can learn a lot by studying these about the sequence of events in the early solar system, how things happened. So by studying these and by studying through astronomy the composition of the sun, we now know what the overall composition of the solar system is. And that's shown in this plot here. This is a plot of the relative abundance of the elements versus the number of protons. And the number of protons is what defines the element. So we have hydrogen over here, which has just one proton, all the way out to uranium over here, the heaviest element. So one of this is what the sun is essentially made of, and each of the planets is made up of a composition pretty much like this. We can't find any material on Earth now that has this composition because the Earth is separated into lots of different layers with different compositions. But how did it get this way? That's a question that people like Harold Urey in the 1940s and 1950s, he's a Nobel Prize winner in chemistry, asked. And we know that hydrogen and helium were produced in the Big Bang. They're still the most abundant elements in the solar system, the most abundant elements in the sun. And fusion of those led to these other heavier elements in a sequence of steps. So that's one thing that you notice as you go from hydrogen and helium down to these heavier elements, they become less and less abundant. That's because each one requires the presence of the ones before it in order to form. And it takes very high temperatures and high pressures to form these very heavy elements. One thing that you notice is these, lithium, boron, and beryllium, have much lower abundances. They're light, they should be, you may think these are pretty easy to make, but they're actually unstable in stars. They're not produced in the Big Bang, so they're present at quite low concentrations in the solar system. Another thing that you may notice is that this curve is not smooth, it's jagged. It's an odd, even pattern. The elements with an even number of protons, and it turns out with an even number of neutrons also, are more stable. Their nuclei are more stable, and that makes them more abundant. These elements, up to iron, are formed by fusion in stars, by fusing successively heavier and heavier elements together. And the heavier elements beyond iron are formed by the addition of neutrons, and those are formed primarily in supernova events. So this is how nucleosynthesis, the creation of elements, in stars works. This is a red giant star, a star much more massive than our sun, at a mature stage of development. This is just before it's about to collapse and explode as a supernova. So there's sort of this onion skin layering where you have different nuclear reactions that are happening. Here's an example of one where nitrogen is combining with helium to create fluorine, and with another helium to create oxygen. So by these fusion reactions, you get heavier and heavier elements. Thank you. And eventually iron and nickel, and that's just before this explodes in a supernova. Here is an image of a supernova about 330 years after it formed, and supernovas create the conditions for forming the heavier elements, things like uranium and thorium. That happens very quickly in a supernova. Within seconds, new elements are formed and they're spread at the speed of light throughout the universe, where they can then coalesce perhaps into other star systems. So this is how uranium and thorium were created in these supernova events. How does this link to plate tectonics? Well, uranium and thorium are the primary heat sources in the Earth's interior. They're what drive plate tectonics. They're what allows the Earth to stay hot still today, 4.5 billion years later. Without them, the Earth would have gone dead after about 100 million years. We also know that supernovas create radioactive isotopes that are very unstable and have short half-lives. Things like aluminum-26. And we have evidence from the meteorites that those were actually present in the early solar system. So there was a supernova event not long before the solar system formed that allowed these to still be alive before they all decayed away. This is an important heat source for melting planets and asteroids in the very early solar system because it decays very rapidly. We know that planet formation is not a gentle process. When the planets were coming together, they are coming together by impacts. There were impacts of large, a lot of times very large bodies, a whole range of bodies. And you can see this on the moon in a way you can't on the Earth because the moon has not been active for a long time. You see these craters and some of these very large craters, the mare, that are now filled with basalts. Impacts were very common in the early solar system. They've become less and less common, but they're important for life even after they became rare. And this is something that Beverly may touch on, Beverly Saylor, next time. But impacts are thought to be responsible for some of the mass extinctions of life on Earth. They also sprinkle in heavy iron-loving elements that are important for many things that without these impacts, these later impacts, all of those elements would be segregated into the core. So things like platinum, precious metals, were primarily brought in after the Earth's core formed very early in its life due to these impacts. We also, let me switch over here, think that the moon itself formed from a giant impact of a planet roughly the size of Mars with the Earth. And this shows a simulation of that type of giant impact. There's a planet rotating around its sun and a smaller one coming in behind it. And here they go. There's an enormous amount of energy that's released when you have a large impact like that that's happening at very high speeds. It's enough to probably melt both bodies completely, vaporize large parts of it, and we think throw off enough material that eventually coalesced and formed the moon.
The moon, about what would be the time frame for the moon to have been formed for that collision that you spoke about? That
we think happened very early in the history of the solar system. Basically, everything was happening within about the first 5 million years or so, maybe 10.
As you had mentioned, the water crystals being present in the zircon at 4.4, so it would have had to have happened before then.
Yes, it happened long before that, probably within the first 5-10 million years of the solar system.
Sort of an elemental question. I noticed you flashed by aluminum-26 and call that a radioactive element. Now, a 700,000 year half-life is not a short half-life to me. That takes quite a long time to decay. So how long was that element around, typically for the life of our planet?
It would have been around in significant quantities. We can detect its presence in the meteorites and the chondrites, but it pretty much decayed away beyond our ability to detect it within about 10, 12 million years. So it's short on a geological time scale. It's actually very useful for providing relative dating of events in the earliest solar system because it has that short half-life. And we can infer how much was present at different times and relatively date events that way.
Two questions. The first, you began with plate tectonics, and I wonder if you could define that. And then secondly, before the Big Bang, is there any evidence within the solar system that there were other universes already present? I'm
not a physicist, so I think that but I'll try to answer your question. I don't think there's any information on anything before the Big Bang. Maybe there was something, but we don't know what it was because everything that we have, space, matter, was formed, we think, in the Big Bang. So this is probably something that's addressed theoretically, but maybe there will be another speaker who can address that. Plate tectonics, I'll talk about later on, but very, very briefly, the Earth's surface is divided up into about 13 different plates that are more or less rigid. Those move around the surface and are recycled back into the Earth's interior. It's the only planet that does that. That's how it loses most of its heat, is by convection of the interior, and that's part of this process where these rigid surface plates go down into the mantle, and it's a continuous recycling and resurfacing of the planet, especially of the oceanic basins. But I'll talk more about that and what that is later on in the talk.
I'm concerned about those 4.4 billion year old zircon crystals. Are they all that small? And if so, how do you find them there in the Jack Hills?
Well, those zircon crystals are actually found in sedimentary rocks. So they eroded out of a mountain belt that was there previously. The erosion, they eroded off and they accumulated in a basin and formed a sedimentary rock. The rocks that they're found in are about 3.6 billion years old. There are lots of different zircon crystals that are found in those sedimentary rocks that can be separated out by various chemical and mechanical means. There's a whole industry that does this because zircons are one of the most important things for dating events in the Earth. So they have a wide range of ages. What people do is look at thousands of these, separate them out, and analyze them all in sequence using an ion microprobe. And they just find the ones, they do a first quick pass and find the ones that are quite old, and then they get better dates on those. This part of the lecture is focused on water. Why is the Earth wet? Earth is the only other planet in the solar system that has liquid water at its surface now. It's the only planet in the solar system that we think has significant amounts of water in any form near its surface. Why is that? And of course, that's one of the factors that makes Earth fit for life. Well, we know that Mars has a dry surface today, although there is some evidence from radar that there's a layer of ice beneath the soil. But we think that there's very strong evidence that it was wet in the past. This looks like some sort of blood vessel or worm tube. I always have trouble with these, but this is actually a canyon. This is on a large scale in Mars. This is perhaps hundreds of kilometers long, a large canyon that have been known about for a long time in Mars. There's been a lot of speculation about them, but they appear, the better and better images we get, they appear to have been carved by water. I can't read that. This is a picture that was returned over here of Mars, that was returned by the Curiosity rover last week. from Mars, and if you look into the sediments there, they look very much like river sediments on the Earth that were deposited by water. They have rounded pebbles in them. They have all the hallmarks of deposition by water. So we think that Mars was once wet, that it had liquid water at its surface, but that water is no longer there. There are other bodies in the Earth's solar system that have long been considered to be bone dry. I don't know exactly what bone dry is, but you see it pop up all the time in the scientific literature, basically meaning as dry as you can get. You can't measure any water in it. If you look at the surface of Mercury, there's no evidence. You can see the craters. You can see some fault scarps where the lithosphere has moved. But you can't find any evidence for water ever having been present at the surface. Same for the moon. We've gone to the moon. We've returned hundreds of kilograms of samples from the moon. And in those samples, also, they were studied very intensively after the Apollo missions, more than any samples in history. And no water could be detected in those samples. Within them, there was no evidence for any water at the surface ever that would have altered those minerals in the lunar rocks. Why is water important? Of course, it's important for biology. We're made of water, primarily. Life requires water. But some other aspects of water that you may not think about that make it very important for planets and planetary evolution are that water can actually dissolve into rocks. We think of water dissolving things, dissolving salt. That's familiar to everyone. But water can actually dissolve into rocks and be incorporated into minerals. Not necessarily as water molecules. It might be as individual hydrogen. It might be as oxygen and hydrogen molecules stuck together, but it can dissolve into minerals. We know that there's a lot of water in the interior of the Earth. We know that the Earth's interior experimentally has a capacity to hold perhaps one or two or more oceans of water. There's a lot of water in the interior that comes out in volcanoes. Well, one of the important things is that water dissolved into rocks reduces the viscosity, reduces the resistance to flow. Rocks on a very long time scale, if they're hot enough, can actually flow like a very, very thick, viscous fluid, extremely thick, much thicker than peanut butter. But on geological timescales, they actually move, and that causes convection, currents in the mantle, which are linked to plate tectonics. Plate tectonics are part of that whole convective cycle. Well, dissolving water in makes the Earth's mantle about 100 times less viscous than it would be if it were completely dry. So that's one of the ingredients that may make plate tectonics possible, is having water around. Water is also very important because it reduces the melting temperature of rocks. All igneous rocks, lavas, magmas, are formed by the melting of rocks. Having water around reduces the melting temperature. This is what causes melting, and this is part of plate tectonics. This is where a slab of solid lithosphere is descending down into the Earth's mantle. So this is part of the crust, oceanic crust. It's descending down. In that process, it releases a lot of water into the deep interior that reduces the melting temperature and causes partial melting. There are volcanoes that are associated with subduction zones all around the world. This is how the melt is produced. It's there because of the water. Water also influences the style of volcanic eruptions. On Hawaii, lava comes out, in general, very quietly and more or less continuously. But when you have a lot of water around, like you do with subduction zone volcanoes, you have explosive eruptions. The expanding steam that comes out of the magma is what provides the energy for those eruptions, and those can have large effects on the environment, and ultimately this is related to plate tectonics. Large volcanoes can release a huge amount of material into the Earth's stratosphere and can change climate. Where did Earth's water come from? An early idea that has long been considered to be one of the primary places is from comets. And the reason people went to comets, we know that they're composed primarily of ice. And also in the inner solar system at the time the Earth was forming, it was too hot to form hydrated minerals, things like clay minerals that have water bound into their structure. So for a long time, people thought it's probably comets. We now think that that's almost certainly not the case, because when we look at comets, when they fly by, we can measure the compositions of their water, the isotopes that make them up. They have a different composition than the Earth's water. So we think that the water actually came in probably from the inner solar system, may have been there from the very beginning, just part of the accretion of the planet. So then we go back to this question, why, and this was sort of the state of the science in 2005, not that long ago. This is Professor Mike Drake, who was at the University of Arizona, and he asked the question, why are there any anhydrous bodies in the solar system? If the water was there from the beginning, not coming in from comets where it may just happen to have hit Earth more, why are there any dry planets? Well, what we're finding now is that maybe the inner solar system isn't quite as dry as we thought it was. Maybe there's actually a lot of water in the interiors of some of these planets. So this is work that I've been involved in recently, where we went back to some of the Apollo samples that were returned in the 1970s and looked at them again to see if there was any water dissolved inside of these materials. This was something that took a while to get off the ground. I worked on this. These are my colleagues who've worked on this project. Eric Howry from the Carnegie Institution in Washington, D.C., and Alberto Sal from Brown University. And Eric had developed techniques with this ion probe that you see behind you for measuring very tiny quantities of hydrogen and other light volatile elements in materials. And so we thought it would be a good idea. Well, let's go back and look at the Apollo samples and see if we can find any water in those samples. Well, that had a lot of resistance. We're all geologists who've worked mainly on the Earth. We didn't work on the moon. There are lots of people who worked very hard on these rocks in the 1970s and did great work. But they were very resistant to the idea. We know the moon's dry. You're not going to find anything. Well, it turns out that we did. We found that there was a significant amount of water dissolved in these glasses. And that provided some of the impetus for NASA. They already had these missions planned to go and look for water on the surface of the moon. Not as water, but as ice, or what we call water ice, because there are lots of different kinds of ice on planets, like dry ice. And sure enough, that was found a couple of years later in a couple of different NASA missions looking at the absorption spectra from these satellites that were orbiting around the moon, found clear evidence for water. There was even a projectile that was launched at these that exploded material out so that the actual water could be measured in those. So there is water on the surface of the moon as well. The Messenger mission to Mercury, it's now in orbit around Mercury, went into orbit, I think, about a year ago. We have a member of the science team in our department, my colleague Steve Hauk, and that has also looked for ice at Mercury. And they think that they've found it. And this is work primarily of another former CASE postdoc, Nancy Chabot, who's another member of the Messenger science team. And these little white spots here are radar reflections. They're impermanently shadowed craters at the Mercury's south pole. Mercury is very close to the sun. Most of its surface is extremely hot. But at the poles, it's very cold because there's no atmosphere to move the heat around. And these look like they're probably ice. That's what we currently think. Back to the moon. How did we discover this water that was dissolved in these lunar volcanic glass beads? This is a tiny little bead of glass that erupted out of a lunar fire fountain type of eruption. It cooled very quickly once it was launched out and traveled probably hundreds of kilometers before landing back on the lunar surface. So we went and looked at this little bead, which is about the size of a period on a printed page, and were able to measure hydrogen, water, across this bead from the center to the edge. And what we found is concentrations up to 30 parts per million, which doesn't sound like a lot. It's really not a lot. 30 parts hydrogen for every million atoms in there, but it's a lot more than people thought was there. And we inferred, based on the profile of water across here, that a lot of it was lost. And this was actually my part of the project, was modeling how much water was initially there that was lost during the eruption process by diffusion of the hydrogen atoms out of that glass bead. And we inferred that there was a lot more present, around maybe 750 parts per million. This was extremely controversial because that would mean these had as much water as lavas on the Earth, and that the moon, at least part of it, may have been as wet as the Earth. We didn't actually measure that, so that's automatically going to make it controversial, but we got a lot of feedback about that no way, it couldn't possibly be that high. Well, then a couple of years later, an undergraduate at Brown, working with Alberto, found olivine crystals that had little inclusions in them of what was magma that then quenched to a glass. When he found these, his advisor Alberto said, "You just got a paper in Science," because these are really critical. They're very rare, but these are protected from loss of the water by being included in olivine crystals. The water can't diffuse quickly through the olivine, so it's trapped in there. And we went and measured these and found even higher concentrations, up to 1,400 ppm water. And now, so it's very clear that at least these have very high concentrations of water, similar to what we find in the Earth. We still don't know if these are representative of the moon. Maybe there's just one part of the moon's interior that's much wetter than other parts, and that's where these are coming from. These are strange magmas in many ways, but clearly there are parts of the moon that do still contain water.
It goes back to an earlier thing you said. You said that if there had not been uranium heating the core of the Earth, I don't remember your words exactly, but to the effect that there would be no life on Earth. Is that correct, that we couldn't live on the surface without heat from below?
Not necessarily, but what would have happened if we didn't have uranium and thorium, we wouldn't have an Earth that was internally active the way that it is now. So we wouldn't have plate tectonics now. The interior of the planet would have cooled off after only, say, 100 million years or so, and it wouldn't be active. So the things that we'll be talking about in the next part about plate tectonics, recycling of material, water is recycled back into the interior, carbon dioxide is recycled back into the interior. All of these things wouldn't happen. And without plate tectonics, is that necessary for life or not? We don't know. It certainly seems to help keep the planet in a zone that it's habitable for longer. One idea about Mercury is very much like Earth. It's almost exactly the same size, made out of more or less the same stuff, but it's a little bit closer to the sun. But it's completely different, unfit for life, has a very dense CO2 atmosphere, which makes it extremely hot at the surface of Venus. No way that there could be life there now. And one of the ideas for why Venus evolved that way is that it lost its water. It was a little bit hotter. The water went into the atmosphere. Once it's in the atmosphere, it can be lost from the planet due to the solar wind. Once that happened and it dried out, the interior dried out, that may have shut off any plate tectonics because it suddenly becomes more viscous. So we don't know. We don't have too many different planets to look at, but looking at the comparison of Venus and the Earth suggests that it's not very easy to get plate tectonics. We don't see it on Mars, we just see it on the Earth. How necessary that is for life, we don't know, but it does provide many of the ingredients.
How are you establishing your dates? And if it's radiocarbon dating, could you explain that a little bit?
Okay, so the dating for the very early solar system is not based on radiocarbon because carbon has a half-life that's way too short. The dates come from various radioactive systems. Probably the most used one is uranium lead, which is used to date those zircons. But there are many other long-lived radioactive systems where the half-lives are billions to tens to hundreds of billions of years, so that they're still present now and can be used for the dating. I could give a whole lecture just on that one topic. There are a lot of different ways that those are dated, but the simplest ones have to do with the accumulation of the daughter product in materials where there initially wasn't any daughter. So for example, if you have uranium decaying to lead, you look at a material that you're pretty sure had no lead in there to begin with because lead's insoluble in that material, and you look at the accumulation of lead in that material from the time that it formed once it stopped losing lead due to diffusion. So at high temperatures, you might lose some of the lead. So exactly what you're dating, you have to look at on a case-by-case basis. For volcanic rocks, most of the ones that I was talking about, they cool very quickly and then they just sit there for a very long time, accumulating the daughter products. And by measuring those, we can date them and knowing what the half-life is. That's in a nutshell. Yep.
Heating effect of the uranium and the thorium in the core, is that necessary for the existence of the magnetic field?
Well, the uranium and thorium are actually, they're in the mantle outside of the core. So they heat up the mantle, and that's what drives the plate tectonics. Whether or not there are any radioactive elements in the core is a question that people have been asking for a long time. Possibly there could be some. It isn't necessary, but it is necessary to have that thermal blanket of the mantle over the core in order to keep it hot. And actually, we're going to talk about the magnetic field a little bit in the very next part of the talk. But yes, it's required in the sense that you have to have a hot planet with liquid metal in it in order to generate that magnetic field. Let's take a look at the Earth's interior, the basic structure of the Earth as it is now. And it acquired this basic structure, we think, very early in its history, not very long after the birth of the solar system. There is a core that's made out of iron, primarily, with some nickel. There's a solid inner core and a liquid outer core. They have almost the same composition, but the inner core is solid because at very high pressure, the melting point becomes very high. There's a mantle that is rocky, but it's like a very viscous fluid. And there's a crust. We have two different basic types of crust. We have oceanic crust, which is made out of basalt, the lavas that come out of Hawaii, for example. And we have continental crust, which is very heterogeneous, but is in general less dense than the oceanic crust. In the core, we think that the core formed very early in the Earth's history. We have examples of asteroids where cores formed within 1 million or 2 years of the beginning of the solar system, of the very oldest materials we find in chondrites. So we think this happened early. There's actually some evidence of that looking at the hafnium-tungsten radioactive system, which I hadn't really planned to talk about, but we have evidence for the core that it must have formed within the first 50 million years or so, and probably earlier than that. Core formation was a complicated process. You know, when you had an impact that formed the moon, there was probably the cores of those two planetary bodies probably merged in that process. So it happened over a period of time. But what we have now is we have liquid metal that's convecting in the core. The liquid metal has a viscosity something like water. Okay, so it's convecting very vigorously as it cools off, and it's electrically conducting, and that is what forms the magnetic field. Not all planets have an internal magnetic field. Earth is one of the only ones that does. We think that Mars did have one in the past, but it doesn't have one now. There's a weak internal magnetic field in Mercury, but of the terrestrial planets, not the gas giants, Earth is the only one that has a strong internal magnetic field. Why is that magnetic field important? Well, we use it for navigation, at least we used to before GPS. And many organisms appear to use it for navigation too. These are little strings of magnetite crystals that were extracted from brain tissue of salmon. Magnetite is a magnetic mineral, one of the only common minerals that's magnetic. These are tiny little crystals of magnetite. They're found in bird brains too, and they appear to use these for navigation. There are even bacteria that produce perfect little magnetite crystals, more perfect than anything that you can grow in the laboratory, that apparently use this to orient themselves in the magnetic field also. Another reason the magnetic field is important is that it protects us from the solar wind. Coming off the sun is a continuous stream of particles, mainly electrons and protons that are coming off at very high speeds, close to the speed of light, and those are very destructive. If those hit the atmosphere, they ionize materials in the atmosphere and then can strip away things like hydrogen. And that's what has happened at the surface of Venus, for example. The water floats up to the surface in the dense CO2, and then it's stripped away. So Venus is now pretty dry. It may have been wet in the beginning because a lot of water seems to have been stripped away by the solar wind. But the magnetic field in the Earth protects us from that. It deflects the solar wind. These charged particles that come in get deflected away in the magnetic field and keep some of them from hitting. And this also is what produces the aurora, the northern lights, is solar wind interacting with the magnetic field. Okay, moving into plate tectonics and what used to be known as continental drift. So we're switching topics a bit here, but this is the primary thing happening. We were talking about the core, which doesn't, aside from the magnetic field, doesn't have a lot of influence on what we experience at the surface, up to the mantle and the crust, the outer layers of the Earth, which do. The core doesn't interact too much with the mantle because it's very dense. It never comes back up to the surface. It isn't recycled. Core formation was a one-way process where the metal descended to the bottom and it just stayed there. It can't come back up. But in the mantle and the crust, there's a continuous recycling, we now know. But for a long time, geologists never considered that this could happen. The mantle, we thought, was rigid. It was made out of rock. And it is rigid on relatively short time scales. We know that seismic waves can travel through them very easily in a way that they can only go through solids. But we now know on very long time scales, it does behave like a very viscous liquid. Well, the early ideas for continental drift, and these are usually attributed to Alfred Wegener, who was a meteorologist, a German meteorologist who spent a lot of time looking at this problem in the early 1900s, but it goes way back before that, pretty much from the beginning of mapping of the globe, all the way back to the 1600s. People have speculated about what you see here, that South America and Africa, the coastlines match up quite well. And if you look at the edge of the continent, which is actually not the coastline where the water is, but out to the end of to the continental slope here, there's an even better match between South America and Africa. So for a long time, that has been food for thought and caused people to speculate that somehow these continents had moved. Well, more and more information on the geology of these regions came up, and Wegener was responsible for putting a lot of that information together. So not only did the coastlines match up well, but the rocks on either side, the rock formations match up between South America and Africa. There are fossils that are only found in South America and Africa. If you look at the present distribution of life, there are a lot of relations between South America and Africa. So there was strong circumstantial evidence that these two were somehow linked by land in the past. And there were ideas about land bridges and that sort of thing. This was never accepted in the United States. It was accepted in the southern geologists in South America, South Africa, pretty much took it for granted that something like this must have happened. And there was a lot of speculation in the United States too, among geologists and in Europe. But geophysicists kept saying there's no mechanism for this to happen. There's no way that continents can plow through the rigid solid mantle. So it really took for this to finally become accepted, a physical mechanism to explain it. And this all happened fairly quickly in the 1960s. The roots of it were in the 1950s, but over a period of about a decade, there was a revolution in the earth sciences, and people went from thinking, no way continental drift could happen, to, oh, this is how it happens. It's plate tectonics. And it was the theory was developed very quickly and was accepted very quickly. The reason this happened when it did probably goes back to World War II, when there was an intense interest in mapping the oceans because submarines were an important part of World War II. And there were technologies that were developed for detecting submarines that were based on magnetic measurements, airborne magnetic measurements, which come into the story here too. But the first thing that happened, there were more and more ocean-going expeditions just to map the seafloor. And what was discovered is there's a huge chain of mountains that are known as mid-ocean ridges in the deep ocean that rise up above the ocean floor an average of about 15,000 feet. So this is a huge mountain chain, bigger than anything in the contiguous 48 United States. And it's a very long mountain chain that wraps around much of the globe. So what was this? The real clincher that led to the development of plate tectonic theory was finding magnetic stripes on either side of these mid-ocean ridges. Okay, so people went out and mapped the magnetism of the ocean floor, and the ocean floor actually, as it forms, I'm kind of getting ahead of the story a little bit, but as this is made out of basalt, and as that magma crystallizes, it locks in the magnetic field that it crystallized in. It's much weaker than the magnetic field, but it records the magnetic field that was present. And periodically, the Earth's magnetic field flips. The North Pole becomes the South Pole, and then it flips back. And what this is showing is different magnetic stripes. This is where it has the polarity that it has now, where the North Pole is the North Pole. In white, that's where it flipped, and this was the South Pole. And then it goes back again. And they're symmetric on both sides. So the explanation for this that was come up with pretty quickly after these were discovered is that the plates are actually spreading apart here. Magma is coming up, it's generated as part of that process of plate spreading, comes up and forms new crust that then locks in the magnetic field. So the prediction then is that this stuff would be very young, and as you go away, it gets older and older and older on either side. People went, collected samples, dated them using mainly potassium-argon dating, and found that yes, that was true. So this is a fundamental part of plate tectonics. This also made sense of an observation that had been made previously, and there were more data coming in, that earthquakes are concentrated in these narrow zones. And here's one along a mid-ocean ridge. These are the plate boundaries. This is where the plates are moving with respect to each other. That's where earthquakes happen. There are also subduction zones, which I haven't told you about yet, but active volcanoes are also associated with those same boundaries where there are earthquakes. Tsunamis are associated with subduction zone earthquakes, and this is a simulation of a tsunami that would happen due to fault motion on the subduction zone in the Pacific Northwest. On the long time scale, Subduction is responsible for building the continents due to the injection of water down into the mantle, causing partial melting. The magmas come up and form new crust. That's one way. And also scraping off material from the ocean crust as the plate goes down into the mantle, scraping off material. Also on the long time scale, subduction is responsible for recycling materials back into the mantle. When the mid-ocean ridges were first found and were accepted to be places where new ocean crust was forming, this caused a problem. Where does it go after that? There were some crazy ideas about, well, maybe the Earth has just been expanding. But that was never accepted by many, and we now have very strong evidence that there are these plates subduct down into the mantle. A lot of material is recycled in that process. At the mid-ocean ridges, there are these geyser systems. Here's a picture of one where water is recirculated through the crust. It reacts with the minerals that are there, and water gets bound into the structures. There are also the shells of tiny little organisms that live in the deep ocean. Plankton fall down in the deep ocean and cover the ocean floor. They're made out of calcium carbonate. And when those go down the subduction zone and they're ejected deep into the mantle, they come back out and they make it back up to the surface, and they are erupted out of volcanoes. So there's a continuous long time scale recycling of material between the oceans and between the atmosphere, subducting it down into the mantle after it's reacted with rocks, and then coming back out in subduction zone volcanoes. So this is the very last slide, and this just shows a reconstruction based on lots and lots of geological data of the last 225 years of plate motion and what that's done to the continents. This is something that'll, I think Dr. Saylor will probably talk about next time, but 225 million years ago, all the continents were assembled together in a supercontinent known as Pangaea, and then they gradually came apart. And we think this has happened several times throughout Earth's history. But the record of that becomes much fuzzier as you go back in time because we don't have the ocean floor anymore. The oceanic crust from those times is all gone now. All the ocean crust is less than 300 million years old. The continents, though, are older, and we can see it in the mountain belts. And I think I'm out of time, so I'll end there.